In this example, we want to begin to look at how to transform a circuit into the Laplace domain. So basically, we're given this problem that we have a 500 ohm resistor, a 16 millihenry inductor, and a 25 nanofarad capacitor, and they are all connected in parallel. And so what we want to do is express the admittance of the parallel combination of elements as a rational function of S. So first, let me say that we'll find the impedances because people think in terms of impedance. Second, let me remind you that elements in parallel, while the impedances combine as inverses, the admittances combine directly. So I don't do a lot with admittance personally. I normally work with impedance. I think in terms of impedance, but it's fine. Basically, the main thing we want to get out of this illustration is how to convert the elements, first of all, into the S domain, and then to do a little bit of a review reminder on what we mean by zeros and poles and how to find those. So we have 500 ohms, 16 millihenries, and 25 nanofarads in parallel. And the first thing we want to do is we want to just pull up our method and go through step by step to transform the circuit. So in step one, and you might want, in watching these videos, to print out or have a second screen where from the PowerPoint presentation you have open that slide that gives analysis method 13.1. So step one, we look to see, are there any initial conditions? In this case, there are not any initial conditions, or all the initial conditions are zero. So the initial current in the inductor is zero. The initial voltage across the capacitor is zero. So I guess my first question to you would be, how do we know this? Your answer might be, well, it's not given in the problem. However, we would know it anyway because we have these three elements in parallel. So if there was any voltage across the capacitor, after these things have sat in parallel for a very long time, the inductor that's in parallel with it would look like a short, meaning the voltage on this capacitor under steady state conditions is going to be zero. Likewise with the inductor current, the capacitor is going to be like an open. Any inductor current would have to go through the resistor, and after a long time, all the current would be drained away. So if this current's been sitting for a very long time, the inductor would have looked like a short, the capacitor would have looked like an open, all of the energy would have been drained out of the system. So all of the initial conditions would be zero. I don't really like the statement there are no initial conditions. The initial condition is the inductor current is zero, the capacitor voltage is zero. We don't have any voltage or current sources, so we don't have to transform any of those. There aren't any voltages or currents that have been defined in this circuit. We just have a network of passive elements, so we don't have to transform those. So since we don't have any initial conditions, basically each component can be represented by its S-domain impedance. So let me review what the S-domain impedance is. For the inductor, that is SL. For the capacitor, that is 1 over SC. For the resistor, it transforms directly as resistance. So we'll have 500 ohms. For the capacitor, we'll have S times L, which is 0.016 S. Just say capacitor. For the inductor, we'll have S times L, which is 0.016 S. And for the capacitor, we'll have 1 over SC, which after we transform that and do a little mathematical simplification, it gives you 40 times 10 to the 6 over S. All of those units are ohms. They're all impedances. They could be combined in series or parallel like we would normally combine impedances. So they can be treated just like a resistor or just like we treated an impedance in the phasor domain. Okay, at this point, we want to substitute each of those expressions in for the elements. So let me show you here. Here is our capacitive impedance. Here is our inductive impedance. Here's our resistive impedance. And so now what we're going to do is we're just going to take the admittance equivalent, which means we take 1 over each of these. So we have 1 over 500 1 over 0.016s, and s over 40 times 10 to the 6th. So all of those expressions for z have flipped. We then find a common denominator and get an expression in the numerator. So you can see what the numerator is, you can see what the denominator is. Now they factor the numerator into these complex conjugate pairs. That might not be obvious to you how to do that, so I'll review that really quickly on MATLAB before the end of the video. But basically what they do is they factor the numerator and it factors into these two terms. And so when you find the zeros, so what are the zeros? The zeros are the values of s that make the numerator go to 0. So you find the factor and you find the roots, and here are the two roots. So those are the zeros. It is okay to have zeros that are complex numbers. You then find the poles, and it turns out that the only thing that would make the denominator go to 0, notice we have 40 times 10 to the 6th s, is if s is equal to 0. So we have zeros, these two places respectively, and we have a pole at 0. So let me exit out of here and we're going to keep this handy so that I can flip back to this and see this function. And I'm actually going to enlarge this so that it's easier for me to see. Get this guy out of the way. And we're going to pull up MATLAB and we're going to try to find the roots of this using MATLAB so that you don't have to know how to factor that. So the numerator is, it is s squared plus 80,000 s plus 25 times 10 to the 8th. So in order to enter a polynomial into MATLAB, now MATLAB was actually originally designed for control theory applications and matrix manipulation. So if you enter that polynomials, and we had a little practice with this in the project. If I enter 80,000, is that right? Is that the right number? Yes, 80,000. So I'm entering coefficients of this polynomial in descending order. Now I have a term for every order. I have a squared, an s, and a constant. If you're missing a term, you have to put in a 0. So we're not missing a term though. And then I have 25 times 10 to the 8th. So 25, 1, 2, 3, 4, 5, 6, 7, 8. Of course, you can enter this using exponents. And now if you want to find the roots of that, you can just say roots, numerator, and MATLAB will give them to you. So there's your 40,000 and your 30,000. It's already giving them to you in the form of the 0 or the root. It gives you I instead of J, but that's okay. And then the denominator, I think that's obvious, but we'll see what MATLAB does if we give it denominator is 40,000. Is that what it was? No. 7 zeros. So 40 million. Okay. 4, 5, 6, 7. And then it's S. So we have to put in a 0 to represent the fact that in that denominator there was not a constant. The constant was 0. And we'll just say roots of the denominator. It should give me 0. I've never used MATLAB to do that. Okay, it's roots. Yeah, there you go. So it's going to give me 0. So I highly recommend in problems like this using MATLAB to help in whatever way you can use it to help, because it's very good at doing these kinds of calculations.